Warehouse automation is really built on one single critical assumption that your physical world, your infrastructure, perfectly matches the digital one, that every single rack, every rail is exactly where the system thinks it is.
So this explainer, it's all about what happens when that core assumption breaks. Because here's the thing. In a fully automated aisle, even the tiniest bit of damage doesn't stay minor for very long. Look, traditional warehouses were built around our incredible human ability to adapt. A forklift operator sees a slightly bent upright and just compensates, right? They tweak their angle, they read the aisle with their eyes, they improvise on the fly. A robot? It just can't do that. It operates on pure trust in the geometry it's been given. And when that geometry is off, the system doesn't improvise, it just faults out.
A good way to think about it is this. Our warehouses has essentially gone from quiet country lanes to high-speed freeways. The rules of the road are totally different, the speed is way higher, and the margin for error has pretty much collapsed to zero. So how does this actually play out? Well, every single automated system runs on a simple, continuous loop. Detect, decide, and execute. The problem is that whole loop is built on an assumption of perfect repeatability. A tiny physical drift in the steel breaks that assumption right at the detect stage, and that one error just cascades forward into every single decision the system makes after that.
Now, if you've ever worked in software, you're familiar with what we call tightly coupled systems. Where a tiny change in one place can cause a massive, unexpected failure somewhere completely different. Well, it turns out steel can behave a lot like software code. Your rack structure is that tightly coupled system. The base plates, the uprights, the rails, the sensors, they are all independent. So a tiny deviation in just one of those components will propagate right on through the entire chain.
All right, let's trace this failure from the beginning. It starts at the floor with a single forklift impact. That impact knocks an upright just slightly out of plumb. That tiny shift then changes the elevation of the guide rail. And that drift in the rail, it creates a positional misalignment for the robot. So when the robot's arm goes to the exact coordinates it was told to, the pallet is now off by just a few millimeters. And believe me, that's all it takes to trigger a fault.
So what does this mean for your team on the floor? It means automation downtime is basically debugging, but in the real world. And just like with software, the bug rarely ever shows up where it was created. It always fails downstream.
So the rack gets hit in aisle 7, but the system faults out over in aisle 12. And without a really systematic way to find the true source of the problem, your team is going to waste hours, maybe even days, just chasing ghosts.
And all this, it really brings us to the heart of the issue. Our existing rack safety standards, they were written for a totally different world, a human-operated world. They're designed to define structural integrity, not the kind of geometric precision that automation absolutely demands. So after any impact in an automated facility, you're no longer just asking one question. You really have to ask two. First, obviously, is it safe? And second, the new, critical question, is it still accurate enough? And look, you absolutely have to answer both of those. If you only answer the safety question, you're leaving a hidden gap in your system. And it's a gap that, sooner or later, your automation will find.
Here's the bottom line. You can't debug a physical system with a 20th century clipboard. If you want to protect your uptime, you need documented precision. At SMHE, we provide the verified data that bridges the gap between structural integrity and system reliability.